Joined Facebook. Between college and Facebook, I worked at an insurance company doing a lot of Linuxy, kind of Python stuff. I joined Facebook in late 2012, and as Nanda said, I joined the SRO team and until about April of 2014, when the SRO team ceased to exist because we automated ourselves out of our jobs with FBAR, which Pedro talked about earlier. I had the opportunity to kind of look around and choose not any team, but choose the team I wanted. And the traffic infrastructure, the global load balancing team was always really interesting to me. So I was very fortunate to be able to join their team. So as I mentioned, I'm a production engineer on traffic. When people ask me what it means to be on the traffic team, this is the first image that comes to mind. It's a visualization of all the users, all the people who use Facebook and all their connections everywhere in the world. Our job on traffic is to make sure that anytime somebody opens up their browser and types facebook.com, or they open up their phone and open up the Facebook app, that they get to a server that's as close to them as possible, and they have the best possible user experience. So quickly, our agenda for today, we're going to talk a little bit about serving dynamic requests. This talk is mostly going to focus on dynamic requests that are going to hit like a real web server. We actually are not going to talk too much about static CDN related stuff. Secondly, we'll go dig a little bit deeper into load balancing at the L4, layer 4, and layer 7. Third, we'll talk about edge pops, how we deploy edge pops throughout the world to reduce latency and provide a better experience for the people who use Facebook. Fourth, we'll talk about our GLB, our global DNS load balancer, and then lastly, we'll finish up with some monitoring and some other stuff. So really quickly, like, what is Facebook from a technical level? Facebook is mainly broken out into two different pieces. We have dynamic requests, which are requests that are actually going to hit a web server. And in our case, it's HHVM. It's the hip hop virtual machine, and it's our the virtual machine that runs all of our PHP and hack code. And it is an open source, something we have open sourced, and we continue to develop on that constantly. And so those are the different types of dynamic requests are like requesting your newsfeed, likes, status updates. The other side of Facebook is static requests. So these are requests that are not going to change each time you request them. So those are static resources, images, videos, JavaScript, and CSS. So here's like a weekly cycle of the egress pattern, egress and ingress pattern from Facebook. So egress is all the outgoing bits per second that we are sending to the internet out of our routers. And this is what the cycle looks like. The top lines are egress, so these are bits leaving our network. The bottom lines are ingress, so those are the bits coming in. So those are the all the requests, and you can see that we obviously send out a lot more bits than we actually take in. So to zoom in and look at one day, these follow a diurnal cycle. And a diurnal is just a fancy word for saying any cycle that follows the sun, any pattern that follows the sun, or any pattern that repeats itself every 24 hours. So every day we have this very consistent egress path. You can see, and these are in Pacific time zones, about 11 a.m. is when we start reaching our first peak. And between 11 and 3 p.m. is we'll come off that peak. And then as the East Coast kind of starts getting off work, you can see kind of another hump there as well. And this is pretty consistent almost every single day. And if we break down this egress cycle, it's actually just a sum of all the time zones in the world. It's really interesting to see the different patterns that different regions of the world actually have. So, and just kind of show like the time zone. Yeah, so the different times kind of equal the sum of the previous post. So some cool traffic stats. Last month we released our year-end 2014 numbers, and at the end of December 2014 there were 1.39 billion monthly active people actually using Facebook, and the average over the entire month of December was 890 million daily active people using Facebook. So this is really cool, like these numbers are great, but as a traffic engineer, I'm thinking in terms of TCP connections and how many requests per second we're getting. And these numbers, they equal hundreds of thousands of TCP connections at any given time. Sorry, hundreds of millions of TCP connections at any given time and tens of millions of requests, which means we are sending out, at peak, many terabits per second of egress. So cool. I wanted to dive in a little bit into just kind of a TCP/IP review, just to kind of to think about the OSI model. Here's an example of, this is the OSI model. So today's talk, we're going to focus primarily on layer 3, layer 4, and layer 7. So layer 3 is IP, Internet Protocol. It's what your routers are routing out all around the Internet. Layer 4 is transport. It's the TCP protocol. And then we'll talk about our layer 4 TCP load balancer. And then lastly is our L7, so the application layer. And we're going to talk about our ProxyGen reverse proxy and focus mainly on HTTP. So here's an example of a layer 3 packet header. A lot of stuff going on. For the purpose of this talk, the only important things are we're going to talk about the source address and the destination address. Here's an example of the TCP header. Similarly, a lot of different bits on here. I cut some of it out. But the only two pieces of information that for the purpose of this talk that we care about is the source port and destination port. And then lastly, here's an example of a very simple HTTP request to facebook.com. It's very simple. So putting it all together, you have your IP, you have your HTTP request encapsulated in a TCP segment, which is encapsulated in an IP packet. But for the rest of this talk, we'll just kind of trivialize it and just and show this, because we don't need all that extra detail. So cool. Now let's talk about serving dynamic requests at Facebook. And before we talk about that, I want to talk about what we're not talking about in this talk. When you make a request to Facebook, and that cloud is all of our load balancers that we're going to get talk about in just a minute, you're actually going to hit an HHVM web server. So this is actually fulfilling your dynamic requests. Each dynamic request could hit tens, if not hundreds, of services on the back end. And for the purpose of this talk, we're not going to talk about any of those. We're not concerned with how we do load balancing on the back end. And we do a lot of really cool stuff, but that's probably like another couple, 3 talks that we just don't have time for. So let's take a look at a Facebook request. If just really simplify it, and assuming we had one web server that served all of Facebook throughout the world. So you're going to open up your phone, you're going to open up the Facebook app, it's going to hit www.facebook.com. It's going to hit a DNS server, and since we're only talking IPv4 today, it's going to return an A record. And then your client's going to actually go out, send that dynamic request to a web server, assuming we'd have no load balancers, and it's going to service that request. So this is a problem because we have 1.39 billion people per month who use Facebook, and we just can't scale it out with one single web server. So how do we get more RPS? We had another layer we had a load balancing layer in here. So we built ProxyGen a couple years ago to offload some of the really core CPU intensive operations that the web server just doesn't need to do. So our L7 load balancer terminates TCP and SSL. So when your request comes in, it's going to hit one of these load balancers, and it's going to look at the HTTP request, and then it's going to send that out to one of the web servers on the back end through an HTTPS connection. And it's already a pre-established connection as well. So this is great, but one L7 load balancer and several HHVMs on the back end can't serve all of Facebook, so we have to add another load balancer. So this is where our L4 load balancer comes in. This load balancer is using the IPVS module, kernel module. It's an open source module, IP virtual server. So your request is going to come in. It's going to come into this IP virtual server, IPVS. It's going to get consistently hashed to one of the ProxyGen servers. So that IP packet is going to be sent to the same ProxyGen host every time. And so that's very important so you can keep TCP. You can keep your TCP connections alive. And then your request gets proxied back to a real web server. So this is great. We can do a lot of packets with our L4 load balancer now, but we need more RPS. So what do? We add another load balancer. So this is actually the last line of load balancers that we have within a front-end cluster. And this is just happening, this is ECMP, so equal cost multipathing, and this is happening from the routers to our L4 load balancers. It's cool. So, and we're actually going to dig in a little bit more in a couple slides. So we'll go into depth on what this is actually doing. So here's a typical example of kind of the scale of a front-end cluster. So we might have tens of shivs, 10 of these layer 4 load balancers, hundreds of ProxyGens terminating TCP and SSL, and then those are getting proxy to many thousands of web servers behind those. So this is really great, but one cluster can't actually serve all of Facebook traffic. So what do? We add another cluster. So this is nice. We have multiple clusters, and we can send traffic to both of them. But now we need redundancy. We need more capacity, and we need redundancy. So what do? Is we add another data center. So our concept of a data center is multiple clusters. And there's a lot of different types of clusters. There's backend clusters, service clusters, database clusters. And like I mentioned in the beginning, we're not going to talk about those for the purpose of this talk. We're just going to talk about front-end clusters that are actually returning requests, responding to dynamic requests. So now we have another data center. We query DNS, and then you can possibly get sent to one or more data centers. And we're going to talk about our DNS load balancer in just a little bit. So one important thing to note, in a lot of these slides, I show this kind of L4, L7, HHVM kind of breakdown. It's linear. This isn't actually how it is in practice. We use it's kind of like Kubernetes or Mesos. We can deploy jobs, and they just run somewhere. We don't really care where. So these jobs actually run, they could be running right beside each other in a lot of the racks. And we'll get to it in just a minute of how we do BGP. So here are different data center locations around the world. We have 4 in the United States, and we have also 1 in Luleå, Sweden. So cool. Now let's get into our L4 and L7 load balancing. So to break it down, again, here's the OSI model. In terms of the OSI, the proxy gen that we talked about before, our L7 load balancer, is at the application level. Our L4 load balancer Shiv is a TCP router. It's routing the TCP connections and making sure they are consistently hashed to the same proxy gen server. And then we have ECMP as well. So here's a typical setup for an L4 load balancer. And again, these could live anywhere in a rack, but just for the purposes of this talk, we'll just show them like this. So all of our L4 load balancers use ExaBGP, and they BGP peer to their top of rack switch, which we do L3 from our top of rack, and they just announced the /32. So that makes that IP available, and that allows the routers to ECMP packets to those hosts. So between the L4 and the L7, what IPVS actually does is it does a consistent hash on all those packets based on the TCP source and destination IP and source and destination port. And we also keep a state table there as well. So just to go through an example, a person's going to Facebook, they send a request, it comes into the L4 load balancer, first it goes to the ECMP, goes to the router, gets ECMP to one of the L4 load balancers, and then that gets consistently hashed to one of the L7 load balancers, and then the request is processed. Another person gets on the app, their request goes through ECMP, Shiv, and ProxyGen, and goes to another server. So now let's just take a look at what happens if we lose one of our L4 load balancers. So that original person is going to send a request, and they're going to get ECMP to the other Shiv server, the other IPVS server in this cluster. And since we are doing consistent hashing, it's going to get hashed to the exact same proxy gen. So you don't lose your TCP connection. You don't lose any state there. Let's look at another example. Say we lose a proxy gen server. So that request comes in. It was originally destined for proxy gen A, but in this case, it's going to actually go to proxy gen B because it's consistently hashed. It's not always the next one, but it will get consistently hashed to another server. So let's say in a couple minutes, maybe we just restarted that process for whatever reason. Say A comes back online and another request comes in. It's going to go to the L4 load balancer. Since we do consistent hashing and we also keep state of all the active TCP connections, it's actually not going to get hashed back to A. As long as it goes back to the same Shiv server, it will actually get hashed back to B. So one important thing that that I didn't mention is we also do DSR, is direct server return. So when these packets go into the L4 load balancer, they're not just forwarded on to the actual ProxyGen server. We do IP and IP encapsulation, and it will get decapsulated, from on the ProxyGen side, and then we'll actually see that in the next slide here. So here's our original request. So this is a original client request, original IP packet, TCP and HTTP. So once it actually hits that L4 load balancer, it will determine what server it should go to, and then it will encapsulate that packet inside another packet destined for the ProxyGen server, the L7 load balancer. So once that packet goes to L4, the L4 load balancer, it then gets encapsulated in an IP packet and sent to the L7 load balancer. So once that packet arrives on the L7 load balancer, since it supports IP and IP encapsulation, it de-encapsulates it and drops that IP back on the networking stack. And the way ProxyGen is actually just listening on this IP, the destination IP, on a tunnel device. So once it gets put back on the networking stack, ProxyGen will pick it up, serve the requests, and then that request will go directly back to the client. So it will completely bypass the layer 4 load balancer. Now this is really important, not necessarily for dynamic requests, but specifically for static requests. We're going to have a very small HTTP request come in, and we might have many megabytes going back in terms of like a photo or a video. So this is actually very important in keeping the L4 load balancer out of the return path. So now we'll get on to edge pops and how we reduce latency by putting servers closer to the people connecting to Facebook. This is an image, a visual showing the average latency, the round trip time internationally around 2011. And this was put together by the traffic team just to determine where was the Facebook experience the worst all around the world. So in trying to make this a much better experience for everybody, we decided to build out our edge infrastructure. And I will show you an example of how we do that. So let's take an example of somebody in Seoul trying to connect to Facebook. And let's just assume they're going back to our Prineville data center. So the TCP connect time to do the three-way handshake is about 150 milliseconds. So just as an example here, we have the person connecting to Facebook, our data center. TCP, you have SYN, SYNAC, and ACK. So since each of these hops are 75 milliseconds, that's going to take 150 milliseconds just to establish TCP. Now we have SSL. There's the five-way handshake there. So by the time TCP and SSL is established, we've already wasted 450 milliseconds of time. And then finally, we actually get to what we wanted to do and actually send our HTTP request. And by the time that HTTP request is sent back, assuming everything works perfectly at the speed of light, it's 600 milliseconds. So what we did was we put a POP in Tokyo, and we did the same thing. Now let's take a look at if we put a POP in Tokyo, if we did the same thing. So here, the TCP connection, it's only 15 milliseconds away between Seoul and Tokyo. So here, after we've terminated TCP and SSL, that happens within 90 milliseconds. And on the ProxyGen layer, we have pre-established connections, pre-established HTTP connections established back to our data centers, and then we just proxy those requests back. So just by putting servers closer to the people who are connecting to Facebook, we've cut the time in half, round trip time, to service their requests. So 600 milliseconds turns into 240. So this is a big win. We have a lot of different edge pop locations around the world, and we're doing as much as we can. We're building them out as fast as we can. So how do the load balancers and the pops actually work? The previous examples, we showed load balancers in the data centers where we had dynamic HHVM servers to process those requests. So what happens is that request goes in, hits the router, gets ECMP hashed to one of our L4 load balancers, which gets consistently hashed to one of our L7 load balancers. And the only difference between a POP and a data center is we actually don't have any HHVM servers to process these requests. So what happens is that request just goes back to an origin data center. So it goes through a router, gets ECMP hashed to one of our L4 load balancers, gets consistently hashed to ProxyGen, and then that request is actually served. So lastly, let's get on to talking about our DNS load balancer cartographer. So again, we have many different edge locations around the world, and we have to make a decision on where we decide to send people when they're trying to connect to Facebook. So there's a lot of different considerations that we need to do to take into account before we decide, before we actually serve a DNS request. So some of them is how close is that user to an edge location. And closeness doesn't always mean physical closeness. You'd be surprised how your packets get routed on the internet sometimes. And other considerations are capacity. We don't have infinite capacity CPU network capacity on our edge locations, so we have to take that into consideration as well. So sonar is how we measure closeness. So we do a very tiny amount of, for a very small percentage of requests, CDN requests, we actually send that request to a suboptimal POP location. And then we measure the time that it takes to actually receive that response. So by doing this, even at a very small percentage, we get so many requests that it actually builds up a really nice map of the internet and all the different net blocks and how close they are away to each of our different POP locations. Our cartographer architecture takes in several different pieces of information, and then it builds a map out of it. So some of the pieces of information it takes in is capacity. Do we have CPU in that edge location to serve this request? Where is the resolver? How close was the resolver to our Facebook resolvers? Did we lose, are there any big internet outages where we've lost internet capacity to our edge location? And lastly, just the general health of the POP. Is it healthy? Is it serving 500s? So all these factors come into play, and then we generate a new map of the world about every 5 minutes. And then from there, that map gets pushed into TinyDNS, which is then the DNS server that serves all the DNS requests for Facebook. Here's another kind of image of the architecture. So we do the offline processing, we generate the map, push it into TinyDNS, and then all ISPs, in general, people who use Facebook will use their ISP DNS resolver, and then from there it gives us also very good an idea of how close they are to our edge locations. So here's an interesting graph of cartographer in action. So the orange line shows the actual demand for a POP. So this is what we would send there if we didn't have cartographer doing any load balancing. This line here, this green one, is the capacity threshold. This is the RPS threshold that we've set that said, cartographer, don't let traffic go above this. And then this squiggly line here is cartographer actually controlling the utilization and controlling the traffic going to this POP. So this shows in very good, it shows the impact that cartographer makes and how well it does in limiting RPS to different locations. Here's an interesting graph showing regional load shed. So this might be just all the POPs in the US, for example. I'm not sure if it is. But you can see clearly here, there's a very visible line that this is the capacity. And you can see that cartographer is not allowing it to go up, to go above that. And it's interesting, you can see the different time zones as well. And then lastly, this is an example of our global load shedding. So cartographer is working 24 hours a day. And we will, if we don't have capacity in a POP, it will send that traffic to the next best guess of where that traffic could be served. So traffic is always doing work and always making sure that we don't overload any of our POPs. So lastly, I just want to talk a little bit about monitoring. We have a lot of internal and external monitoring. So we do monitor TCP state. We also do some L7 monitoring to check the different protocols that we use. And it's extendable. So if there is a new protocol that comes along or a new service that needs, say, MQTT, it's very easy to extend that. These are geographically diverse, all the services that are external that are monitoring our systems. So these live in a lot of different data centers off of our network. So if we notice a big outage, if several of these external monitoring systems notice that our POP in France is down, then it will actually automatically drain a POP, and we won't even have to know about it. Nobody has to. Well, we will get woken up, but it will get popped, or it will get drained before there's too much damage. Another thing that is really useful is our server and client-side monitoring. We do, in general, when we're on call, we look at very few metrics, or we get paged on very few metrics. Since we are Internet facing, a lot of the metrics that we do look at are direct impact that it could be causing a user to have a really bad time. So we look at client latency, client errors, are we serving 500s, 503s, and also egress. The graph that I showed in the beginning is a very good indicator. If egress drops by a couple hundred gigabyte, that's a problem and we need to fix it really quick. Some other really nice things is Cartographer does real-time RPS monitoring as well. So you saw that line and how it did a really great job of keeping it close and keeping the utilization right at that line. We do have collection agents going out and collecting data in real time. And lastly, we do a lot of peering all around the world. So we do monitor our POP, transit and peering, and also backbone utilization as well. So with that, I wanted to highlight some of the open source projects that we use. We have open sourced our ProxyGen HTTP libraries. So these are the core libraries that are actually doing the parsing of all the requests. TinyDNS runs all of our DNS infrastructure throughout Facebook. IPVS, IP Virtual Server, is an open source kernel module, and we are actively committing upstream to that. ExaBGP is what's used on all of our Shiv servers to actually announce the /32 and make them available via ECMP. And Python is the glue that holds Facebook together. So we use the heck out of Python, and I thought it deserved a mention up here. So with that, thanks. Any questions? Yeah. Any questions about load balancing or anything? Yes.
Question about health checks and service discovery. How do you configure your L7 proxy gens to find new backends, HHVMs or whatever you use?
Yeah, so we have a configuration distribution framework, and those are continually pushed out. So if there is a problem, it will be a configuration will be pushed out to all of our servers, and it will know that the next hop or the origin data center is down or shouldn't receive as much traffic as before, and it will limit its RPS to that accordingly.
I'm curious about communications between IPVS and...
Oh, okay. Between IPVS and the L7?
Yeah.
Yeah. So IPVS is the kernel module that we use to do the actual IP and IP encapsulation. Shiv is which I kind of use them interchangeably, is kind of our wrapper around IPVS, which is using it's what's actually doing the health checks. So we have static configurations for all of our, actually I take it back. We have service discovery for all of the L7 load balancers based on Zookeeper. So those Shiv servers will actually health check all the servers in service discovery. And it will actually mark them down. If it sees it down, it will actually mark it down.
Cool, thank you.
Yep.
Hi, so my question is, after the connection comes to the L7 load balancer, so that's where the TCP connection's terminated, do you then speak HTTP into the company, or do you use your own RPC mechanism?
HTTPS, yeah.
Okay.
So we have pre-established HTTP-S connections to a lot of the servers, to the backend servers.
Oh, they're pre-established?
Yeah.
Okay, because I was going to say that sounds like you wouldn't, you would then have more latency issues, but you...
Nope, yeah,
you
we
do
have a
connection
pre-established
caching
pool of
after that.
connections that will be used to just forward that request on.
Okay.
Yeah, and that's especially important in the POPs. So we don't have to wait for that, that 150 milliseconds to establish that. Yeah, they're all pre-established.
Okay, thanks.
Yep.
I was just curious, how do you guys handle DDoS?
That's a good question.
Yeah, because you mentioned this thing, right?
And specifically, where do you attack?
Where do you attack? I could probably defer this to Doug Porter in the back there. I hate to say it, but it's not really that much of a problem. And I shouldn't have said that, but we definitely do. We do see it, and we do get it from time to time. And generally, it can cause a bad experience, especially if they're hitting a very targeted like edge location. So they can cause a bad time for some period of time. But yeah, I haven't seen a successful DDoS for our entire infrastructure. So.
One more question.
We've DDoSed ourselves. So by far, so to answer your question, we DDoS ourselves more than, like we've caused ourselves a lot of pain, like having a lot of mobile clients try to reconnect and they can't and they just keep crushing our servers. So we definitely DDoS ourselves from time to time.
One more question, please.
Sure.
So when the user connects on, let's say, HTTP to Facebook,
Yeah.
it gets converted back to HTTPS, right?
Yeah. I don't even I don't even know if we do HTTPS 100%.
Right. So at what point does it get converted at the POP, or does it go all the way back and then?
I think we're going to immediately switch it over to HTTPS. But all of our connections between client and our servers and between our servers and our data centers are all encrypted. So it is HTTPS back to our origin data centers.
Okay. All right. Thanks.
Did that answer it? Or?
Yeah, it does.
Okay.
During that slide where you showed taking out a layer 4 load balancer,
Yeah.
it sounded like you said the user doesn't lose the TCP connection; that still holds on. I was wondering how that happens.
Sure.
Do they share the TCP state among all the L4 servers, or what's happening there?
So when we lose an L4 load balancer, it's still going to go through ECMP. So when that packet comes in, it's still going to, since ECMP is flow-based ECMP, so it does look at the TCP connection, it should get hashed to the same L4 load balancer. So your question is, what happens if it doesn't, if it goes to a different load balancer?
Right.
Since it is a consistent hash, and as long as those have the same idea of all the L7 load balancers under it, it will get consistently hashed to the same server.
Okay. So I'm thinking, so the user has done like SYN, gotten a NAC back, and he's established a TCP connection. And now HTTP was flowing to some server.
Right.
The L4LB drops.
Right.
All right. I'm thinking he still has to establish another TCP connection. It sounds like you're saying that doesn't have to happen.
Correct. Yeah, so it's gonna, if this load balancer goes away, if this one goes away,
yeah,
it's still gonna go through this load balancer. And since they all have the same number of proxy gens underneath them, as long as there hasn't been some drastic change in the L7 load balancers, it's gonna consistently hash on the source IP, source port, destination IP, destination port.
Right.
Since it is a consistent hash, it doesn't matter which server it goes to, it should get consistently hashed to the same server.
Okay.
So you won't lose your TCP connection.
Just as a follow-up on that, the TCP is actually established with the L7 load balancer, which is why the L4 going away doesn't break the connection. My
Correct.
question is, on a later slide, you talked about using ExaBGP for your BGP connections. Did you investigate Quagga, and is there an advantage for ExaBGP versus Quagga?
I'm not sure specifically if we've investigated Quagga. I know what is nice about ExaBGP, it's very scriptable. We don't really need to run a full daemon. We just need to like scrape the routes, or in this case, just send a /32. It's really simple to do that.
Yeah.
So I mean, it's Python. It's really easy to use.
It kind of sounds like any casting. I'm sorry, there's another term for it. I've forgotten the term, but yeah.
Because you have so many layers of load balancing, how do you deal with ICMP fragmentation needed packets?
That's a good question. You're going to have to come talk to me after. It's a good question. I'm not going to be able to answer that one. We need Alex Gartrell here for that. Cool. No more questions. Let's drink beer.